Legged robots offer unique advantages over wheeled or aerial robots in that they can navigate complex terrain and accommodate non-trivial payloads. Manipulators can be added to legged robots to further allow them to interact with and change their environment. These new manipulation forces must be considered when planning for these systems, as the same forces which enable manipulation may also contribute to instability of the platform. To this end, we introduce the Stability and Task-Oriented Receding Horizon Motion and Manipulation Autonomous Planner STORMMAP. A user defines motion and manipulation tasks, along with pre-specified contact locations. The desired velocity is used to compute a sequence of support polygons along the optimization horizon. These are used in the zero moment point stability criterion. Next, a nonlinear optimization problem is constructed, whose constraints ensure dynamic feasibility and stability of the robot, while the costs incentivize the completion of user-defined tasks. The output of this are the continuous motion and force plans, which are sent to the robot's controller, which computes the joint torques for the robot. STORMMAP generates plans in less than 10 milliseconds on average, allowing the planner to run in a receding horizon fashion. The speed of the planner also means that disturbances to the robot can be perceived and mitigated before they cause instability.
The following experiments, along with the plots of the force at the manipulator, are shown to demonstrate the versatility of STORMMAP.
Here, we want the robot to push a table across a room at a constant velocity. When using a planner which does not account for the manipulation forces, the robot is able to push the table, but cannot maintain a forwards velocity at the same time. Using STORMMAP, the planner considers the desired tasks and computes a plan for the motion of the robot and force at the manipulator. It is then able to both push the table forwards and walk forwards at the same time. To make this more challenging, we also apply a random unknown disturbance to the robot perpendicular to the direction of motion during the task. STORMMAP perceives the disturbance and modifies the manipulation force plan to counteract this disturbance force, and continues to apply this force to bring the robot back in line with the table. For a better look at the disturbance mitigation properties, here we can see a user apply forces to the body of the robot which are unknown to the planner. The robot can perceive these disturbances and apply forces to the railing to counteract these disturbances and remain in place. Next, we show STORMMAP utilizing a railing to remain stable as it walks across a slippery floor. This experiment demonstrates the ability of STORMMAP to use its manipulator to stabilize itself in challenging situations. As the robot walks, it modulates its manipulation forces against the railing to help stabilize itself. It also uses these forces to propel itself forwards, which helps avoid slipping at the feet. STORMMAP has shown its versatility in a variety of situations. By removing the need to compute computationally expensive contact locations, STORMMAP can generate plans in less than 10 milliseconds on average. To the best of our knowledge, this is an order of magnitude faster than existing legged mobile manipulation strategies in the literature.